Hello everyone. Today I'll be trying to implement a program that adds numbers from m to n, uh, both included, such that m is an integer less than n. So, but we have one restriction, and that restriction is that we should not use branching mnemonics that are already in ARM assembly. Instead, we should be using our program counter. Uh, and program counter, as you know, is a register, our 15th register, that shows where the next instruction is going to be. And thereby it executes all the instructions one by one in our algorithm. So by changing the PC, we're able to change what the next instruction that is going to be executed will be. And by doing that, we can replace the branching mnemonic that's already in ARM assembly. So, in order to first understand the problem, I don't want to get into the details of PC counter, program counter and stuff. So I'll implement this program as we would normally do this. Let's start by first defining our variables. So we had m, n, and we wanted to find the sum of the numbers from m to n. Let's set our R0 register as m, and our initial value is going to be 1. Why 1? Because it's just easier to calculate that. I'll add comments just to make it easier to go back and understand. So m is going to be the starting integer. Now we're going to have r1, which is going to be our n. Let's make that 5 because we know what 1 plus 2 plus 3 plus 4 plus 5 is, which is 15. And we can use the sequence, the sum of a sequence formula. So n is going to be our ending integer. Now let's have our accumulator variable. I'll put this in R2 because this is sum. We should start from 0. Our sum. Now, I'll label this just for ease to understand. Now let's have our loop. So, let's think and see. How would we do this? We would, in most of the times, we would use a for loop because we know how many times to execute, or we can also use a while loop. It doesn't really matter which loop we use in C because in the end it's not going to change anything much. But in assembly, since we don't have a lot of registers, dedicating another register just for an incrementer is unnecessary. Instead, we can use our R0 register, increase it until it's equivalent to n, and stop after it exceeds n. And the reason we don't stop when it's equal to n is because we want to add the number n as well. So it's going to be 1 plus 2 plus 3 plus 4 plus 5, not from 1 to 4. We include both of the numbers. But in a for loop, what we usually do is just assign I to this number, iterate over each number, and when we reach a great number greater than n, we stop. And that is just to preserve the value of m, but we'll not need the value of m here, so we can just change it and make a more efficient loop. And since ARM assembly doesn't have a lot of registers, As the complexity increases, this is not the most scalable solution. Therefore, I'll use a while loop. And the way we do a while loop is basically the same as using an if loop, except we will have a few, maybe only one additional branching statement that just continues the conditional statement, so to speak. So we'll first start by comparing the values of R0 and R1, and the reason is basically this is going to be while n is less than or equal to n. And I explained why it should be equal to. Now let's compare the values of R0 and R1. This will store the result in an NZCV register, and to check for conditions, we'll use that register. Now I'll do the weights it is implemented normally, the most standard way, and then we'll look at some other solutions we can implement. Now, what we usually do in assembly to make it closer to code in C and any other languages is to reverse this condition, and when that reverse condition is satisfied, we just exit the loop. So we would have an end label here, and we would do svc2, our service call, to end the program, end the program, or something else, depends on what our program is, but here we don't have anything else, so I'll just end the program. And the process would be more correct. Okay, so that's why I'll use greater than, I'll append greater than GT to the end of our mnemonic, which is the opposite of this statement. So I'll do BGT, so branch if greater than, and now I'll branch to end. So if this value, the value of m, which we increment each time, exceeds the value of n, we just get out of the loop. It's like a break statement in C, if you know what I'm talking about. Now, we did the conditional part, and now we should look at what else we do inside the loop. Since we're just gonna exit the loop if this condition is not satisfied, we don't have to add any append anything to other mnemonics here. So I'll add the number m to R2, add to R2 the value of R2 and the value of R0. And each time the loop executes, we want m to be incremented. So this is basically sum plus or equal n m, to be more correct. And then we do add to R0 the value of R0 plus 1. So this is just incrementing number. So m plus plus. I don't prefer that notation because it implies something else. That's the m plus equals 1. Now, after we end these operations inside, we have to loop back. And the way we loop back is through B. I'll use an unconditional loop because the program would have already ended if the condition is not satisfied. Now let's run this code. just for sanity check. We put 0 to R0, 5 to R1, and we start comparing. It doesn't get out of the loop. It adds the sum, it increments the value of R0, and then it loops back. Let's repeat this until the program ends. So program ended, and let's see this in decimal. So this is 15, and we expected that. This is one more than n, which we also expected because it only stops when m is greater than n. So everything is going well. What now let's think of any optimizations we might do to this. So as you might already know, having a lot of branching statements is not good for the execution of the program, and I'll explain the reason why. But the reason is because each time a program goes through the code, it builds momentum, and this part is going to be the part I'll explain later. And when we encounter a branching statement, we basically don't know what the next instruction is going to be, which slows down the program would be more correct, which slows down the program, and it's not really the most efficient way. Another way to implement this in ARM assembly is to get rid of the statement, because the code inside this, once finished, will basically go here. So there is no point in adding an explicit statement that just ends the program, because in any case the program is going to run this. Now I remove this, but without this the program is not going to work correctly. I have to make sure these only run if this condition here is satisfied. And to do that, I can just add le less than or equal to, which is the same as this condition. I'll do this for this one, and also loop, because I don't want this loop to be infinite. I want this to be only done when this condition is satisfied. And after this whole loop ends, this is not going to run, this is not going to run, and this is not going to run. And the program is going to end. The process is going to end. Now let's run this. So it should execute this. Yeah, it did, as R2 changed. Now R0 changed. So we're looping back. Let's repeat once more. So we reached 6, and it compares. Now these are not going to run, and they don't, and our program ends. So we got 6, 5, 15, which was what we expected. Now we are done with our main implementation. Now let's think in terms of the PC, the program counter. So how might we go about implementing this? So we know that branching is basically changing the PC to this value. So let's see what that value is. So it is C, which is the number 12 in decimal. So instead of using this, I'll remove this, and I'll move the code. As you see, I also added this because I don't want this to be executed when the condition is not satisfied. So now I'll move the PC the program counter to the number 12. This, and we can also see it's 12 here, decimal. Now, let's see how it works. Now it's 5. I think one last execution. And yeah, the program ends. We got 6, 5, and 15. It works correctly. But there is one problem with this implementation, and that problem is if we add a line, the whole thing collapses. Let's see. I want to make another variable, and let's set this to number 4. Let's try this again. As you can see, this is already 16 in decimal. It's actually hexadecimal, so I converted. Now, let's see where this leads. At least back to this one. Now, in this case, it's not a big deal. This is just a constant. We're not working on the variable R3. But is this the most sustainable, scalable way? No. So let's think of any other alternatives. Instead of statically putting in this number, we might think of a dynamic way of changing our PC. One way is to know where this is. How might we go about that? So we can find this by just, so we know this code comes after this, right? This if you had the code here, this code would this line would come after that line. So if you just move to I'll use R5 here because the actual instructions show that. And also the PC counter here. This will be our address variable, address point. I don't know how to express it. So this will be our point, and every time we are here, we can just move the PC to this value. So if this is at this value, it would be running this code, but we don't want that, so we do add le. We want to add just one line worth of bytes to this, so we can just run this. And there's a reason I actually used the number 4 here, because that is the bytes per word size, and each instruction is a word long, so we'll need that. So we'll add to PC the value of R5 and R3. So loop back. Let's run this. So now R5 should be 16, but it's not. It's 8 more than that. Let's go on about this program and I'll explain what that is later. Why is that 24? It's really weird, but after I explain, it's going to be really clear why. And it's going to reveal a lot of things about how a CPU works. So when we compare, everything goes as expected. this as well, but once we reach here, we add to our program counter, which is 32. We will store in our program counter the value of R5 plus R3, and that shows this line, which we don't want, which we want this line, the address 14. So why did this happen? So when a CPU works to maximize the efficiency, it prefetches two instructions in advance. So the reason it does this is because in every fetch, decode, execute cycle, we lose some time. If we wait for the code to be executed, we lose some time. Instead, we can like prefetch certain data and execute, and like every time we do that cycle again, we can just feed in the stored instructions and to speed up the process. And this is what I referred to by this is what I meant by momentum beforehand. It means that the program just fetches the instructions before, so when the next instruction has to run, it doesn't have to go all the way back to the memory and fetch once again. It can just use the stored instructions that is already uh, fetched by the CPU beforehand. But when there's a branching instruction, it just has to flush uh, all those instructions in the pipeline, because it cannot predict what the next instruction is going to be. So it just has to branch and see whatever comes. So to account for that, we should just know that our PC is actually 4 more than we expect, and in this case it is going to refer to the instruction after the next one, which is this one. So by subtracting 4 from this number, so from R5 we're going to subtract R3, our bytes per word size, and since this already pointed to this instruction, if we subtract 4, it's going to point to this instruction, and this instruction is the instruction we want to run here. So let's compile and load. Let's see what happens now. Okay, we go from yeah, R3 is 4, R5 is PC. So as you can see, R5 is 24, and this instruction is at 20. It's 24, so 24 points to this instruction. We run as we normally do, and then we subtract R3, which is equal to 4. So our PC is now at the start of the loop. Let's continue this just to check. So it should not run this time, and the program ends 6/5/15. What you expected. So this is a dynamic method. We can do this just by adding this, storing the value of PC at this point. But the thing is, if we add something else here, let's say I added some, I don't know, I summed two numbers, stored the values of, okay, add R4, store the value of R0 and R1, and here, this is not the best implementation because it's now going to point here. then we'll run this instruction. So in most cases, it's better to keep this inside the loop. So we always guarantee that the instruction after this one is the start of our actual loop logic. And these are variables are just for setup. By the way, you can just do, if you want to use it for something else, or just initialize the variables beforehand, you can just do this. So we're not losing anything here. We're not losing anything from our functionality. So let's run this to check. So let's see where our PC R5 points at 28. And now in the end we get 24. So it went here, which we wanted to implement. Now the sum is also 15 and it ended the loop. So our program works. Thanks for listening. This was the end. And I hope you learned a lot through this process, a lot about how pipelining works, how a PC counter points to the next instruction, and why is it more than we expect when referring to the value. And this goes to show that we usually take a lot of things for granted when we're using layers of abstraction, and how fascinating it is in reality when you implement it for yourself and see that something as simple as just moving the counter and like looping back is very complex in when we really look at it. So I hope you learned something from this video, and you understand how many layers of abstraction there is, even in assembly, which is considered one of the closest languages that is actually comprehensible by humans, um, and are close to and is close to the human language while still being very close to the hardware level. And even in such a simple language, we see that there are a lot of abstraction layers involved, which put a barrier between the CPU and us. Thanks for listening.